You probably think mirrors flip left and right. It feels obvious. You stand in front of one, lift your right hand, and the person in the reflection lifts what looks like their left. Case closed, right? That's what everyone learns as a kid. But hold on a second, because this everyday assumption is actually wrong. Mirrors don't reverse left and right at all. And once you see why, you'll never look at your reflection the same way again. Think about your morning routine. You walk into the bathroom half awake, pick up your toothbrush, and stare at the person in the mirror doing the same. You blink your right eye, and the image blinks what looks like it's left. Your instinct says the mirror swapped your sides. But ask yourself something simpler. Why only left and right? Why not up and down? Your head stays at the top in the reflection. Your feet stay at the bottom. The vertical direction is untouched. So how does a perfectly flat sheet of glass decide to treat one axis differently from another? It doesn't. The mirror has no idea what left or right even mean. It doesn't recognize directions, and it certainly isn't programmed to flip one but not the other. Light just travels straight from your face, hits the mirror, and bounces back. That's all. The reflection is simply the result of geometry. If something appears reversed, the cause must be somewhere else. And that somewhere is your brain. Let's test this carefully. Imagine holding a book up to a mirror. The letters appear backward, so it feels like left and right swapped. But look closely at the object itself. The left edge of the book in your hand lines up with the left side in the reflection. The right edge stays on the right. The top stays on top. The bottom stays on bottom. The mirror didn't shuffle anything sideways. The light rays didn't crisscross or twist. They simply bounced straight back to your eyes. So if nothing actually crossed from left to right, where does the reversal come from? The answer is depth. The mirror doesn't swap left and right. It swaps front and back. It reverses the direction pointing toward and away from you. Imagine pressing your face against the glass. Your nose, which sticks forward into the room, now appears to stick backward into the mirror. The same thing happens to every part of you. The mirror inverts the depth axis, the direction perpendicular to the surface, and leaves everything else unchanged. A good way to picture this is with a glove. Take a right-handed glove and turn it inside out. Suddenly it becomes a left-handed glove. Nothing moved sideways. You just flipped the inside and outside. That's exactly what the mirror does to space along the direction you're facing. It turns that axis inside out, and the rest follows naturally. But here's the interesting part. Even though the mirror only flips front and back, your brain insists on translating that into left and right. Why? Because of how humans move. When you see your reflection, you subconsciously imagine stepping into the mirror world to face that person. And how would you do that? Not by flipping over like a gymnast. You would walk around and turn to face them. That turn swaps your left and right relative to the mirror image. The rotation happens in your imagination, not in the glass. In other words, the mirror didn't change your sides. You mentally rotated yourself, and that rotation created the illusion. The mirror just reflected light. Your brain did the rest. And once you realize that, a simple bathroom mirror stops being simple at all. Now, this might sound like a small technical detail, the kind of thing you nod at and forget 5 minutes later, but it actually reveals something deeper about how we interpret reality. The mirror isn't confusing anything. It follows the rules of geometry perfectly. The confusion comes from the way our minds reconstruct the world. We don't just see what's in front of us. We interpret it through our own habits of movement and symmetry. Human beings are roughly symmetrical, left to right. One arm on each side, one eye on each side, one ear on each side. Because of that symmetry, our brains naturally compare one side of our body to the other. But we are not symmetrical, front to back. We have a face on one side and the back of our head on the other. So, when we see a reflection, the only way our mind can make sense of it is by imagining ourselves turned around to face it. That imagined rotation swaps our sides in our mental model, even though nothing physical in the mirror actually swapped. If our bodies worked differently, the illusion would change. Imagine a world where humans moved by rolling instead of walking, like logs turning on the ground. If that were how we moved, our instinct would be to imagine flipping over instead of turning sideways. In that world, people would grow up saying mirrors reverse up and down, not left and right. The reflection wouldn't feel sideways. It would feel upside down. The mirror would be exactly the same, but the interpretation would change because our biology changed. This tells us something important. What feels obvious is often just what feels familiar. The laws of physics don't care how we move or how we interpret images. Light travels in straight lines, reflects at equal angles, and returns to the observer. That's it. Everything else is psychology layered on top of geometry. And this isn't just a philosophical curiosity. The idea that reflections involve a deeper symmetry leads directly into one of the most profound questions physicists ever asked. Does the universe itself care about left and right? Or are those directions fundamentally interchangeable? For centuries, scientists assumed nature didn't care. The equations of motion, gravity, and electromagnetism all work the same if you swap left and right. If you filmed billiard balls colliding on a table and then showed the mirrored version of the film, there would be no way to tell which one was real. Both obey the same physical laws. The universe seemed perfectly ambidextrous, but this assumption created a strange thought experiment. Suppose you made contact with intelligent beings somewhere else in the cosmos. You want to explain to them which side of the human body the heart is on. You can tell them our height, our weight, or the wavelength of hydrogen to define units of length. But how do you define left? You can't use directions like east or west, because their planet might spin differently. You can't refer to the direction screws turn, because their tools could be threaded the opposite way. You can't point, because they can't see you. Without a shared visual reference, how do you define a direction that only makes sense relative to your own body? If physics treats left and right as identical, then there would be no way at all. No experiment, no measurement, no signal could distinguish one from the other. In that case, the idea of left would just be a local convention, like choosing which side of the road to drive on. For a long time, that's exactly what scientists believed. They thought nature had no preference. They thought symmetry between left and right was absolute. Then someone asked a dangerous question. What if it isn't? What if somewhere in the laws of nature there is a tiny bias, a subtle preference that breaks the symmetry? What if the universe itself has a handedness? That question didn't stay theoretical for long, because once you ask a question like that, you can design an experiment to answer it. And when the experiment was finally done, the result stunned everyone. The universe, it turns out, is not perfectly symmetrical after all. To test whether nature truly treats left and right the same, physicists needed a process sensitive enough to reveal any hidden asymmetry. Ordinary mechanics wouldn't do. Colliding balls, swinging pendulums, orbiting planets, all of those look identical in a mirror. The laws governing them are perfectly balanced. If the universe had a preference, it had to be hiding somewhere deeper. Attention turned to one of the strangest forces in physics, the weak nuclear force. This force operates inside atomic nuclei and governs certain types of radioactive decay. It's subtle, difficult to measure, and mostly invisible in everyday life. But precisely because it acts at such a fundamental level, it was the perfect place to search for any built-in handedness in nature. Two physicists, Li and Yang, proposed something radical. They suggested that maybe, just maybe, the weak force violates mirror symmetry. Maybe the universe actually distinguishes between left and right at a microscopic level. At the time, this idea sounded almost absurd. Symmetry had been treated as sacred, but science advances by testing even uncomfortable ideas, so an experiment was designed. The experiment was carried out by physicist Chen-Xiong Wu. She used atoms of cobalt-60, which undergo radioactive decay by emitting electrons. First, she cooled the atoms to extremely low temperatures so their motion would be minimal. Then she placed them in a strong magnetic field, forcing the atomic nuclei to line up in the same orientation like tiny spinning tops all pointing in one direction. Now came the crucial test. When these nuclei decayed, they would release electrons. If nature were symmetrical, Those electrons should come out equally in all directions relative to the spin, but if there were a hidden bias, the electrons would prefer one direction over the other. When the results came in, the symmetry shattered. The electrons did not emerge randomly. They showed a clear preference for one direction relative to the spin of the nucleus. In other words, the mirror image of the experiment would not behave the same way. The reflection would predict outcomes that never occur in our universe. It was a stunning discovery. Nature itself distinguishes between left and right. The universe has a handedness. This meant something extraordinary. For the first time, there was a physical process that could define an absolute left and right anywhere in the cosmos. If you were communicating with aliens across the galaxy, you could now explain the difference. You would tell them how to perform this decay experiment, and whichever direction the electrons preferred would define one orientation. From that, left and right could be determined unambiguously. Of course, there's a twist. If those aliens were made of antimatter, the result would flip again. Antimatter obeys mirrored rules for certain interactions, so an antimatter civilization performing the same experiment might define left opposite to ours. If you ever met such beings in person, shaking hands could end very badly. Matter and antimatter annihilate on contact, releasing a burst of gamma radiation. It's a humorous thought experiment, but it highlights how deeply these symmetries matter. What started as a question about bathroom mirrors had led straight into the foundations of particle physics. The mirror on your wall reflects geometry, but the universe itself contains asymmetries that run far deeper than reflections of light. Some interactions care about orientation in a way that space itself seems not to. And yet, when you stand in front of that mirror each morning, the image still feels like a simple left-right swap. That feeling persists because your brain is solving a biological problem, not a physical one. It's trying to map the reflection onto a body it understands. It isn't analyzing coordinates. It's imagining motion. Once you recognize that, the mirror stops being mysterious and starts becoming a lesson. It shows how easily intuition can mislead us. The world behaves according to rules far simpler and far stranger than the stories we tell ourselves about it. And sometimes, the path from a toothbrush and a reflection leads all the way to the weak nuclear force. Once you realize that the mirror itself is innocent and that the reversal lives in your interpretation, the everyday reflection becomes a doorway into something much larger. It reminds us that what we perceive is often filtered through the structure of our own bodies and minds. The physics is straightforward. Light travels, reflects, and returns. But the meaning we assign to what we see depends on how we imagine ourselves inside the scene. When you look into a mirror, you don't just observe geometry. You project yourself into the image. Your brain asks how the person in the glass relates to you physically. Because you normally face people by turning around horizontally, that imagined rotation becomes part of how you interpret the reflection. The result feels like a swap of sides, even though no such swap ever occurred in the light itself. This difference between physical reality and perceived reality shows up everywhere in science. Our senses evolved to help us survive, not to reveal the underlying structure of the universe. They give us useful approximations, not perfect descriptions. That's why we have to build instruments, equations, and experiments to see beyond our immediate intuition. The mirror is a simple example of that gap. It obeys a clean mathematical rule. One coordinate, the depth, changes sign. Everything else stays the same. But our brains convert that into a story about left and right because that story fits how we move and interact with the world. It's not wrong in a practical sense. It's just incomplete. And once you start noticing that, you begin to see how often our mental shortcuts shape our understanding of reality. We describe the sun as rising and setting, even though it's the earth rotating. We talk about heat as a substance flowing from hot to cold, even though it's just energy moving between particles. We say mirrors reverse sides, even though they simply reverse direction in space. These descriptions work in everyday life, but they hide the deeper mechanics underneath. This is where physics becomes more than a collection of formulas. It becomes a way of stripping away those shortcuts and asking what actually happens beneath the surface. When we do that, even familiar objects start to look different. A mirror is no longer just something for checking your hair. It's a demonstration of coordinate transformations. It's a reminder that space itself has structure, and that orientation matters in subtle ways. And the implications stretch far beyond the bathroom. The same principles of symmetry and reflection help physicists understand fundamental interactions, particle behavior, and the geometry of space-time. The question of whether a system behaves the same under reflection isn't just philosophical. It's a test that reveals the inner workings of nature. When symmetry holds, the mirrored version of an experiment is possible. When symmetry breaks, the mirror image describes a world that can't exist. That distinction tells us something about the underlying laws governing particles and forces. The discovery that the weak interaction violates mirror symmetry showed that the universe isn't perfectly balanced. There are built-in asymmetries that give direction to certain processes. So the next time you stand in front of a mirror, you're not just seeing yourself. You're witnessing a tiny demonstration of how geometry, perception, and physical law interact. The reflection is simple, but the meaning we assign to it reveals how our minds work. We don't just observe reality, we interpret it. And sometimes, the difference between those two is where the most interesting insights live. Once you understand that the mirror is not flipping your world, but simply reflecting light along a reversed depth axis, the everyday scene in your bathroom becomes something much richer than it first appears. You are no longer just looking at a duplicate of yourself. You are watching geometry at work. You are seeing how space itself can be transformed while still obeying the same physical laws. And this realization should make you pause, because it shows something deeper about how we understand reality. The universe does not come labeled with human-friendly directions like left and right. Those are concepts we impose because of the way our bodies are built and the way we move through space. Physics, on the other hand, only cares about relationships between positions and motions. It describes transformations, not preferences. The mirror teaches us that what seems obvious is often the result of interpretation rather than fact. It also reminds us that the universe is consistent, even when our intuition is not. Light obeys precise rules. Geometry follows strict patterns. But our brains convert those patterns into stories that make sense to us as humans. That translation is useful, but it can hide the deeper truth. And once you start thinking like this, the world changes. You begin to see that many puzzles in physics are really puzzles about perspective. Is something moving, or is the frame moving? Is time flowing, or are we moving through it? Does the mirror reverse space, or do we mentally rotate ourselves to match what we see? These questions sound abstract, but they shape how we understand everything from motion to relativity to the structure of the cosmos. The mirror, in a way, is a small training ground for scientific thinking. It invites you to question what appears obvious and ask what is actually happening. It shows you that explanations based on everyday intuition often miss the real mechanism underneath. And when you learn to look past that first impression, you begin to uncover the elegance hidden beneath ordinary experience. So tomorrow morning, when you step into the bathroom and catch your reflection, don't just see a familiar face staring back. Think about the path the light took to reach your eyes. Think about the coordinate that flipped sign while the others stayed the same. Think about how your brain is interpreting that transformation and translating it into the idea of left and right. That simple moment is a reminder that the universe is full of subtle rules, operating quietly beneath the surface of daily life. You don't need a particle accelerator to encounter them. Sometimes all it takes is a pane of glass and a beam of light. Science isn't only about distant galaxies or abstract equations. It's about learning to notice what is already in front of you and asking deeper questions about it. The mirror doesn't just show your appearance. It shows how your mind interacts with reality. And understanding that interaction is part of understanding the universe itself. If this changed the way you look at something as ordinary as your reflection, then it did its job. Because the goal of science isn't just to collect facts, it's to sharpen the way we see. Thanks for taking this journey with me. If this made you look at the world a little differently, share it with someone else who might enjoy seeing the familiar turned into something new. And next time you stand in front of a mirror, remember, nothing flipped except your perspective.